here is the one of two typical ways of drawing the XYZ coordinate system, where the axis coming out at you is the x-axis, the axis to the right is the y-axis, and the axis going up is the z-axis. Sorry, 1 second here. Here's the link to the attendance form again. So what I generally kind of think of is that corner in the room being the origin right here, where all the axes meet. And then this kind of edge along the floor here coming out towards you in the sense is the positive x-axis. This edge along the floor in front of us is the positive y-axis. And this edge going up here is the positive z-axis. The ones I've drawn the arrows on are the positive axes. So this is still the x-axis back here, just the negative side, y-axis negative side, z-axis negative side. I will often also felt like I think of the YZ plane as what's on the paper, and the X stuff is what's shooting out towards you or shooting away from you. This is the way I usually draw it. Some people prefer to draw it like this, which I don't absolutely love, but it works for some people. I'm not a fan of that personally, but that works for you. And definitely, I think someone in the 16C class I'm co-costing for also does it that way. So it's not like what I will remind you of is, and you can do kind of all sorts of things. So sometimes people rotate this 90 degrees like around the z-axis, and so they will maybe do it like this instead on occasion. They'll say, here's your positive x-axis, here's your positive y-axis, and here's your positive z-axis. That is also allowed. The only thing you actually have to make sure you remember to do is obey what's called the right-hand rule. The right-hand rule, which you'll learn more about in physics, I think, basically says you put your fingers on the x-axis. What I should say, you use your right hand. That's why it's called the right-hand rule. Fingers on the x-axis, curl your fingers towards the positive y-axis, and your thumb should point in the direction of the positive z-axis. So if some things switched around, just be careful. All right, so how to plot things in 3 dimensions? Well, it's kind of boring. I'm not going to lie. It doesn't feel very exciting to plot points in 3 dimensions, but we should still talk about how to do it because it is sometimes useful or necessary. So here's my XYZ axis, or coordinate system, I should say. And let's say we want to plot the point 2, 3, 5. And we don't really want to just eyeball it. Here's what I'll say. The YZ plane part is the part that is acting kind of normally, for lack of a better term. So going some distance in the Y or Z is going to look the same. Then I'm going to want to go 3 in the Y and 5 in the Z. Because of course we are marking this in lexicographic order or alphabetical order. This is, X, Y, Z. Now, the x-axis, on the other hand, has been essentially tilted, right? You took a thing that was as long as the other thing, and then you kind of rotate it like this. Look at me for a second. You took something this long and then turned it like that. Does it look as long as it was? No. So the thing is, the marks on the x-axis have to be kind of closer together to still represent the same length. Kind of weird, but it's true. So these are going to be kind of closer together. But because of the idea of perspective, right, that's what we're doing. So then we're going to go 2 in the x direction, 3 in the y direction, and 5 in the z direction. And the order doesn't really matter. We want to be careful. So 2 in the x direction, 3 in the y direction, 5 in the z direction. And then I want to kind of combine that all together. So typically what we do is, after you've chosen one direction, then you go another direction. So like I can go 2 in the x, and then I'm going to go 3 in the y. So from that point, 2 in the x direction, I'm going to move exactly 3 units over in the y direction. Or from the point that's 3 in the y direction, I'm going to move 2 in the x direction. Moving in the x direction is always kind of the hard part, in my opinion, because you have to be sure that you move parallel to the x-axis. So from here, this is where having a ruler is actually not a terrible thing. I'm just going to move parallel like that. So there's the point where I've moved 2 in the x direction and 3 in the y direction and none in the z direction. Or I could go 3 in the y direction and 5 in the z direction. Or 5 in the z direction and 3 in the y direction. Here's the point 0, 3, 5. Or I could go 2 in the x and then 5 in the z. Or 5 in the z and then 2 in the x. So that's the point 2, 0, 5. And finally, I can kind of fill in the rest of this box and go, well, 3 that way, or 5 that way, or 2 that way. And there is the point 2, 3, 5. I kind of think of it as the opposite corner from the origin of the box that has all those dimensions. So this is a box where this length is 2, this length is 3, this length is 5. One corner is the origin, and the corner opposite the origin is the point I was looking for. You probably don't have to draw quite this much to locate a point in 3 dimensions, but if someone wants you to be kind of specific about it, you can't just kind of like eyeball it. You kind of need to guide. I think people call these guidelines. You should draw these guidelines if you're trying to draw a point in 3 dimensions. There's not a lot more to it, to be honest. Why don't you all try on your own for a second? Try drawing the point. Draw the point. Say, I don't know, let's go negative in the next direction. Let's say we're going to go -2, 3, 2, 4. Try drawing that point on your own. I'll give you a moment. All right, let's take a look. This isn't bright enough. So I'm going 3 back. So -3 in the x direction. There's the point -3, 0, 0. +2 in the y direction. 0, 2, 0. +4 in the z direction. 0, 0, 4. And then we're kind of finding where all these things meet. So I'm going to kind of go this way. I'm going to go this way. Great. Then I'm going to go back 3 parallel to my x-axis, which again, I'm not great at doing. I often like to grab a little ruler. That. And then I'm probably going to do a few more. I'm going to go 2 to the right this way, back 3 that way. See where these meet up here. And that might be enough, right? I don't feel like we have to draw the entire box. So I could say, great, yeah, I've gone -3 in the x direction, +2 in the y direction, oops, and a +4 in the z direction. But you could also go from here and then back like that and then over like that if you really feel like you have to draw the whole thing. I don't know. It's hard to know what level of the detail people are really going to expect. I wouldn't say probably too much. I will also point out you can plot a point in GeoGebra. It doesn't look very helpful though. Like, great, there's a point out there. If you line up your axes, it does kind of help. So you can see here, if here we're looking at, say, whoops, I had it. Looking at kind of the XZ axis here. Oh yeah, that looks like I've gone negative 3 in the x direction and positive 4 in the z direction. Or if I turn it this way, it looks like I've gone positive 2 in the y direction and positive 4 in the z direction. Or if I turn it, can I turn it? Maybe. Be challenging here. Maybe not. I want the z-axis to point out at us. Maybe. Oh, there we go. Now it looks like I've gone negative 3 in the x direction and positive 2 in the y direction. So yeah, it looks like I've got the right point. It just isn't super, like just a point in space. It's like, okay, well, yeah, maybe it's in the right spot, but it's not easily to visually tell. All right, let's say a few more things. What else to say about graphing in 3 dimensions? Oh yeah, one thing to be aware of is in 2 dimensions, let me zoom back out a little bit. In 2 dimensions, we have quadrants. And they're nicely labeled. The first quadrant is over here, quadrant 1, and then we go counterclockwise, quadrant 2, quadrant 3, quadrant 4. And specifically, quadrant 1 is the quadrant where x and y are both positive. In quadrant 1, x is greater than 0 and y is greater than 0. In 3 dimensions, we don't really have an ordering, but we do have octants. So each axis divides the kind of thing into 2, and when we do that 3 times, you get 8 divisions. And so the first octant is often where most of our pictures are. The first octant is where x, y, and z are all positive. But there is no kind of standard labeling of the rest of the octants. So I wouldn't have no idea of what, like, is the second octant the one to the left or to the back or to the, like, it's just, no one has ever talked about that really, as far as I know. But often the reason I point that is because some people will be like, graph this shape in the first octant. We often cut off our shapes in the first octant because they're just easier to draw that way. Let's talk about graphing a few other things. So we have the coordinate planes. You are already very familiar with one of them, the XY plane, right? That is the plane that we've done all of our 2-dimensional graphing in probably up to this point. The XY plane is what I'm going to call the floor. So here's our XY plane down here. And on the XY plane, the only thing that's true is that z is equal to 0. Right? You can't go up or down, but you can go as far left or as far right or as far forward or as far back as you want. Any point in the XY plane has an x coordinate and a y coordinate and a z coordinate of 0. Similarly, in other coordinate planes, you have the same kind of thing happening. So back here in the YZ plane, well, then you haven't moved forward or backwards. So in the YZ plane, you have that x is equal to 0. It's very similar in 2 dimensions how we have axes, right? The y-axis is just the line x equals 0 in 2 dimensions, and the x-axis is just the line y equals 0 in 2 dimensions. Same idea here, there's just an extra dimension of freedom. And lastly, we have the XZ plane, where y is equal to 0. Great. And then you can have other planes. So you can set, well, in fact, there's lots of ways of writing the equation of a plane, but other planes that are parallel to these coordinate axis planes or coordinate planes, you can just set one of your variables equal to a constant. So for example, the plane, say, z equal to 6. You're just shifting this XY plane up 6 units, right? Every X and Y can still be anything you want them to be, but the Z part is now 6 higher. So if I go up to a height of say like 6, Here's the 0.006. And I'm just gonna have a plane. So I'm gonna extend in the directions that are parallel to both y and x. Again, parallel to x is always a challenge for me. Here too. Here's a plane. There's e equal to 6. You just shifted it up. Now, I should point out, obviously, I'm not drawing the whole plane. I couldn't, right? It's an infinite surface. It goes on literally, just like you never draw the whole line, right? We draw some arrows. You don't usually draw like little arrows at the ends, though, even though it goes on forever. We just kind of draw it, some amount of it, and then you're done. In a similar sense, we could draw a plane parallel to the XZ plane. We could draw, say, like, I don't know, y equal to 4. I'm just shifting 4 over to the right and going 1, 2, 3, 4. And then I'm going to take that point and I'm going to extend it in the directions of the variables that are not in my equation. Right? Y equals 4, great. Y is set. Z can be anything. So I can go as far up or down as I want. And X can be anything. I can go as far forward or backward as I want. Do it. Pretty good. Certainly, some people are better drawers than others. So I always feel like teachers can't really ask you to do much drawing on an exam because it's just like, well, some people are just not good at drawing stuff. So take that for what you will. I think there is some expectation of being to kind of identify surfaces. So we'll talk about it a little bit more. And then I guess just for completeness here, let's do one more. Let's say we wanted to graph the x equal to 2. So now we're just moving 2 in the x direction. So we're going 1, 2, and then we're going to go as far left or right as we want and as far up or down as we want. Because you're playing x equal to 2. It's kind of fun to draw them. Like, I won't lie, drawing in 3 dimensions can be interesting, but it can also be tedious. So planes are one thing, and then I'll say, so most planes we draw often are parallel to one of the coordinate planes, but they don't have to be. For example, let me give you 2 more planes. So I kind of think of a plane as being like the 3-dimensional equivalent of a line. For a line, everything has to be raised to either the first power or the 0th power, right? X equals 5 is a line, y equals 2 is a line, or y equals 3, x equals 7 is a line. In 3 dimensions, if you have everything raised to the first power or not at all, you get a plane. So for example, we could have something like what? Like x plus 2z equal to 5. There's a plane. I don't have any y, meaning I can go as far left or as far right as I want because the y can be anything. I'm going to draw this line first in the xz plane. Did I pick a good line? Maybe not. I don't know. So let's see. So if z is 0, x is going to be 5. And if x is 0, z is going to be 5 halves. And so here is the line. Use a different color here. It goes to those points. And now we can extend that line as far left or right as we want in the y direction. So here's our plane. And if you go left, I don't recommend drawing it left and right. Like you could draw it more to the left as well, but it starts to kind of, at least my pictures start to kind of fall apart if I draw too much of them. So you can have a plane that kind of goes through 2 points on 2 of the axes. You can also have a plane that has all 3 variables. For example, we could have something like 2x plus 3y plus z equal to 6. And when you have all 3, typically the way we deal with this is just to draw, well, I'll show you. So here's my x, y, z coordinate system. And if I'm graphing a thing, typically I want to find all of my intercepts. I kind of shot myself in the foot there, but that's all right. So I'm going to set x and y equal to 0 and get z equal to 6. I'm going to set x and z equal to 0 and get 3y equal to 6, which is going to give me y equal to 2. I'm going to set y and z equal to 0 and get 2x equal to 6, so x is equal to 3. So I've got those 3 intercepts, and then I'm just going to connect them. And I really, even though I know there's more to this plane than just this triangular looking section of it, no one really draws more than that. Like you could try to draw more, but it usually does not go well for me. But yeah. All right, enough about planes. Now trains. Now sphere. So let's look at an equation of a sphere. X squared plus y squared plus z squared equal to 9. This is a sphere whose center is at the origin and whose radius is the square root of 9. Not too terrible to draw. And honestly, here's how I would draw it. I would deal with what's happening in the YZ plane first, because that's the plane that looks like just graphing on the paper. So in the YZ plane, well, great. I'm going to have a circle of radius 3. And so then we can try our best to draw it. You could get a compass, I suppose, if you really wanted to. I mean, but no. And then I'm going to draw my circle in the YZ in the XY plane, just kind of like a flat circle. And honestly, here's what I would do. I wouldn't mark it out. I was going to be like, well, I'm going to try and draw a circle from here to here. I'm just going to do this. That's pretty good. And then back around as well. And then you might, if you want to, label that point and that point. So here's the point 3, 0, 0. Here's the point -3, 0, 0. Here's the point 0, 3, 0. Here's 0, -3, 0. And here's 0, 0, 3. And 0, 0, -3. We don't really need to label all these points, but it's kind of nice to see that they are there. More generally, just like the equation for a circle is usually like x minus something squared plus y minus something squared equal to the radius squared. Same idea, we're just adding another dimension here. So we're going to have x minus h squared plus y minus k squared plus z minus l squared equal to the radius squared. And this sphere, this is the equation of a sphere with center h comma k comma l and radius r. Very, very much like the equation of a circle. Just we're adding something here. It is interesting to me, or at least it was interesting when I learned it way back when, that this is still just the radius squared here, right? There's no like extra cubing or something. Like I always was like, why is it like something else there? But it's actually because of how the distance equation works. When you're finding the distance between 2 points, it doesn't matter how many dimensions they have, the equation is still the same. In fact, let's talk about it. So distance between 2 points in 3 dimensions, let's say x1, y1, and z1. And wow, those are ones? Yeah, those are ones. And x2, y2, z2 is the usual thing. It's going to be the distance is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And so if you're trying to find the, say, in fact, let's find the equation of a sphere centered at 0, 3, -2 with a radius of 4. Admittedly, we could just throw that into the formula. But I will point out, because I think it's worth pointing out, the whole idea about a sphere and a circle is that it's just all the points that are some distance away from the center. So the sphere is literally every point that's 4 units away from the center 0, 3, -2. So we think about it that way. Here's my sphere. Here's my center 0, 3, -2. And any point on the surface of the sphere, x comma y comma z, well, I know that whatever point I have, whether it's here or there or there or there or there, the distance between that point and the center has to be 4. So when I say, well, my distance is the square root of x minus 0 squared plus y minus 3 squared plus z minus -2 squared, and that's equal to 4, because that's what the distance formula says it has to be. Well, then if I square both sides, I exactly get the equation of the sphere. I get x squared plus y minus 3 squared plus z plus 2 squared equal to 4 squared. And that's where the equation of the sphere really comes from. It's just you're taking the distance formula and say, oh, well, the distance between my center and any point on the sphere has to be this. That's what the equation is. Questions so far? I mean, I feel like it's relatively straightforward, most of the stuff. It's just kind of boring, I think. I mean, it's kind of interesting to draw. Some of the pictures look nice, but for the most part, it's kind of like, yeah, this is real exciting. So, but let's skip through it because we have to, and then we can finally talk about vectors. Couple other things to say here. Yeah. Oh, I know. One more example here. What is the center and radius of the sphere below? Given by x squared plus y squared plus z squared minus 6x plus 8y minus 2z equal to, sure, 16. So don't get fooled by this. The radius is definitely not 4. 100% not 4. Because we haven't written this equation of our sphere in the standard way. So what we have to do here is complete the squares. So I'm going to write this as x squared minus 6x. So I want to group all the like variables together. I'm going to leave myself room for what I know I'm going to fill in. Plus y squared plus 8y, and again, leave myself a little blank there, plus z squared minus 2z. And whatever I end up adding here, here, and here, I'm also going to have to add to the other side as well. So hold on for just a second. So to complete the square here, I'm going to take -6 divided by 2, which is -3, and square it. That's going to give me a positive 9. If I add 9 there, I'm going to add 9 over here. For y squared plus 4y, y squared plus 8y, half of 8 is 4, 4 squared is 16. Add it to one side, add it to the other side. Finally, z squared minus 2z, well, half of -2 is -1, and -1 squared is +1. All right. X squared minus 6x plus 9 becomes x minus 3 squared. Y squared plus 8y plus 16 becomes y plus 4 squared. And z squared minus 2z plus 1 becomes z minus 1 squared. And on the right hand side, I get 16 plus 9 plus 16 plus 1, which ends up being 42. So my center is positive 3, negative 4, positive 1. My radius is the square root of 42. And that just is what it is. All right, let's see. What's happening there? Okay, I got some time still. So, yeah. Sure, we'll do one more sphere question because I feel like spheres we often talk about. So one more question would be to say, find the equation of the sphere with a diameter whose endpoints are, make up something. Hopefully it's not going to suck too much. -3, 1, 6, and let's say 7, 5, -2. So those points are the endpoints of a diameter. So to find the equation of the sphere, what do we need to know? The center and radius. To find the center, if you have the diameter, the endpoint of the diameter, you're just finding the midpoint. Or what I really, honestly, I never call it the midpoint formula. I just think it was the average. You're averaging those 2 points. So the midpoint, aka the center of this sphere, is just the average of those. So it's going to be, let's see, -3 plus 7 over 2, 1 plus 5 divided by 2, and 6 plus -2 divided by 2. Be careful that you are always adding these together. Sometimes people subtract them accidentally. So here we're going to get -3 plus 7 is 4, 4 over 2 is 2. 1 plus 5 is 6, 6 over 2 is 3, and 6 plus -2 is 4, 4 over 2 is 2. Cool. Then you have a choice. You can either find the distance between these two endpoints and say that's the length of the diameter, and then cut it in half. Or if you found the center, you can find the distance between the center and either one of those two endpoints. That's usually my preferred way of doing it. Let's find the distance between the center, 2, 3, 2, and either point you want. It doesn't matter, you're going to get the same result. I'm going to do 7, 5, -2. Let's see, that distance is going to equal the square root of 2 minus 7 squared plus 3 minus 5 squared plus 2 minus -2 squared. That's going to be the square root of -5 squared plus -2 squared plus 4 squared. Okay, so that's going to be the square root of 45. Also, one reason I don't like doing it the other way, like if we, so just to point out, if we had done it the other way, if we found the distance between the endpoints, so the distance between the endpoints would be, I will just tell you, it would be the square root of 180. And dividing that by 2 is kind of a pain because you don't want to like write divide root square root of 180 divided by 2. You want to simplify, but then you have to like pull out the square factor and just kind of like. All right, so then the equation would be x minus 2 squared plus y minus 3 squared plus z minus 2 squared equal to my radius squared. And yeah, I would just write that as 45. Feels silly to write it as a square root squared. There's the equation of our sphere with those diameter endpoints. Okay, I think we've talked about spheres enough. Let's talk about a few more graphing things and we'll call it a day. Yeah. Let's see here. Sometimes, yeah. So let's want to be on screen. What I want to be really. Let's give a geometric description for the set of points that satisfy the given conditions. I honestly feel like this kind of setup is more geared towards web work questions, which none of you have, right? You all have, oh, you are gonna be doing web work. Interesting, okay. Well, that's good. It's good that he's listening to you all. I certainly thought his homework assignments were good, but hard. And probably also, have they been graded yet? Not the second one. Yeah, I imagine it was not a small amount of work for someone to grade all those homework assignments. They, at least I don't, I mean, unless they were doing a bad job. Anyway, and your class is not using web work either. They're using the other one, yeah, which is fine. But this kind of question feels more like a web work style question. So what about my lab? Yeah, I mean, they both have their upsides and downsides. My lab, certainly, you really have to kind of walk through every step. And sometimes you're like, but I just want to get this right. I don't want to do all the, but also, but I do think my lab is good. So, yeah. So let's see, what if we describe this as the x equals 2 and y equals 4? Well, I know that both of those are planes, right? X equals 2. In fact, we probably should graph. So here x equals 2. Way out here. And maybe I should have done y equals 4 first. Oh well. Let's say over here, that's where y equals 4. Y equals 4 is the plane that goes in the x and z direction. So if I need to meet both of these conditions where x equals 2 and y equals 4, I'm just getting this line where they intersect. On this line, it is always true that x is equal to 2 because you're always 2 forward, and it's always true that y is equal to 4 because you're always 4 to the right. But since z isn't even in any of the equations, you can always move as much as you want in the z direction. That's kind of something I would really take to heart with all this, is that if you're not seeing one of the variables show up in your equation or your whatever, that usually means you can move as much as you want in that direction. And let's kind of, let's look at this next one. We'll kind of talk about that. So let's say I had the equation x squared plus y squared equal to 4 and z equal to 0. Okay, x squared plus y squared equal to 4 is what kind of shape? Circle. And z equal to 0 just means we are in the xy plane. So I'm just drawing a circle in the xy plane. So I'm going to go 2 to the right, 2 to the left. I'm actually not going to mark out 2 forward and 2 backwards. Here's what I'm going to do instead. I'm going to try and draw the circle right now, but a flat circle, right? It's not like a in your face circle. It's you put it on the ground and try to draw perspective. So I'm going to try and go like this, like that. I guess I don't need to do a dash because, and then I might label those points if you really want to. There's 0, 2, 0. There's 2, 0, 0. There's 0, negative 2, 0. There's 0, sorry, negative 2, 0, 0. Not necessary to label them, just I like labeling them. Contrast this with the equation x squared plus y squared equal to 4. And that's it. Well, now z can be anything. So you don't just get a circle, you get a circle that then you kind of extend as far up or as far down as you want. In other words, you get a cylinder. So I'm going to do the same sort of thing. First, I'm going to draw this circle in the xy plane. But then I'm going to say, but then it can go up and down as much as I want. So it's going to go like up like that. Or down. And again, right, technically it could go on forever and ever and ever. So there's your cylinder with the circle of radius 2 extended in the z direction. Fun fact, not fun fact, terrible fact, actually, not my favorite fact. Let me show you what I mean. let's say I wanted to graph. Sure, let's say we wanted to graph y equal to x squared, which is a parabola. And hopefully I don't mess it up too much. Here's my x-axis, here's my y-axis. It's looking kind of like this. And there's my parabola in the xy plane, but I didn't say anything about z. That means that we can go up or down as much as we want. So I'm going to extend this up kind of like this. And then the same thing that way. And you know what we call this thing? A cylinder. Dumbest stuff I've ever. It's I don't like the thing is you basically take any kind of not straight line, any kind of curve in 2 dimensions, and if you extend it in a 3rd dimension, we call it a cylinder. This is technically called a parabolic cylinder. But basically, take any shape you want and extend it in another direction, and we call it a blank cylinder. So you could have like an elliptical cylinder or a hyperbolic cylinder, or any shape you like, just stretched in another direction is called a blank cylinder. Feels kind of dumb, but I didn't make it up, so don't blame me. Sure. Draw a few more things. Because as much as I like this kind of stuff, I feel like this section actually there's not a lot of like drawing these cylinder shapes. So let's look at 1 or 2 more things. Oh yeah, drawings get harder. Let's say we want to draw x squared plus z squared equal to 9 and y equal to 0. Oops, sorry, you can't see that. That's a circle, but now it's in the xz plane, which is probably for me the hardest plane to draw in. So again, circle of radius 3. So I'm going up 3, going down 3. Here I might go, yeah, I might label the 3 in the x directions as well. So I'm going to go 3 in the x direction. Again, in the x direction, it's not going to look as big. And try your best to draw that circle. Yeah, that's all right. It's not going to look like a circle. It's going to look like an oval, right? Because it's going to look like you took a circle. Somebody's looking at me. So you took a circle and you tilted it like that. Now it doesn't look so circular from our perspective, but we still know it's supposed to be a circle. Okay. Oops, water everywhere. Yeah, sure. A couple more things. Let's say I wanted to graph. I had some numbers. You know, just random numbering every once in a while. Sure. Let's say we had something like this: 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 2, 0 less than or equal to z less than or equal to 3. That's a lot of points. It's all the points inside a box. So if I was trying to draw this, I will say often when we know that everything is positive or non-negative like it is here, sometimes we only draw the first octant. Like sometimes I wouldn't draw like all this, this, and that. I would just draw the positive axes. That's totally fine. So let's see here. X can go from 0 to 1. Y can go from 0 to 2. X can go from 0. I didn't give myself enough X room here. At least not if I want to keep my scale the same. X can go from 0 to Z can go from 0 to 3. So I basically have just a cube. The only difference between this and like drawing the points is now I'm going to kind of fill in the whole shape, which feels, I don't know, like a waste of ink maybe. Here's my box that I would have drawn if I was trying to find the point 1, 2, 3. And then it's all of that. So scribble away to your heart's content, everything in there from front to back. I don't know. That's not my favorite thing to do. It's kind of feels kind of silly. I'm like, yeah, it's all, I mean, I could write words. It is the box that contains those points, but yeah. Sure. Yeah. Let's set up what we're going to be doing next time, because as much as I think really to do yourself justice here, you just need to practice it. And again, I don't know how much your professor is going to ask you to do. A lot of the web work questions that you guys might now see that you're going to do web work will ask you to like take, like they'll give you these equations and they'll be like, tell us what we're describing with these equations. So like if this is my question, I'll be like, well, we're describing all the points inside a box. Or we could ask something like, let's say we have x squared plus y squared plus z squared less than or equal to 4 and z greater than or equal to 0. Well, x squared plus y squared plus z squared equal to 4 is a sphere of radius 2. Less than or equal to 4 means all the points inside the sphere of radius 2. But z being bigger than or equal to 0 means we have to be above the xy plane. So it's kind of like the top half or a hemisphere. So this is the top half of a sphere of radius 2. So we could draw it. And I'm going to opt to draw the thing that's in the YZ plane first, because that to me is just the easiest. I'm going to go 2 to the right, 2 to the left, 2 up, not 2 down because Z can't be negative. And so I'm going to draw that semicircle. Wow. Am I going to draw a semicircle? I'm going to try. And then I know it's also going to go in the X and Y in the forward and backward direction. So I'm going to kind of draw like that. There's my hemisphere. And I guess I could scribble inside it to indicate that I have all the points. Again, I don't really like doing that, but
just half of the sphere.
it's, well, so I would actually say it's half of a ball. Because we often use the words, so when someone says the word sphere, they mean only the points around, like the peel of an orange. Where if they say ball, they typically mean all the points inside as well. So the orange flesh as well as the peel of the orange. Which I don't love that particular language personally, because if someone's throwing a ball to you, it's usually not a solid ball, right? Like there's not, I mean, there are like a softball is pretty solid, but a basketball is full of air. So when I hear the word ball, I still kind of tend to think about something that's more spherical. But in math, when we say sphere, we mean just the exterior. When we say ball, we mean the interior points as well. So here we have half of a ball because it's all the points, not half of a sphere. Yeah. All right, let's call it a day.